These videos have been produced on site in a large fabrication facility, and we ask your understanding for the environmental background noise. The Copper Development Association is pleased to present a series of video presentations covering the welding of copper-nickel alloys. This video is the second in a series designed to provide welders with the principles of joining 90-10 and 70-30 engineering grades of copper-nickel. Here we consider TIG welding. To recap, in our first video, we covered preparation for welding. Maintain a high level of cleanliness and avoid contamination, which can cause weld cracking. Preheat and post-weld heat treatments are unnecessary. There are elements that even in small amounts are very detrimental to copper-nickel alloys, and if present on the surface before welding, they can cause embrittlement and cracking. The elements that are particularly harmful are lead, sulfur, phosphorus, and other low melting point metals. The fabrication of copper-nickel alloy pipe and tubes is similar to that of other alloys such as carbon and stainless steels. We are assuming that all viewing this video are familiar with the basics of welding, and our message is to point out where the copper-nickel alloys are different and exceptions are needed.
In this section, we'll be demonstrating gas tungsten arc or TIG welding of copper-nickel plate. We've prepared two pieces of 90-10 copper-nickel as we showed in the last segment. Notice that this is a tight root joint with a 70-degree included angle. We've spaced these plates above the fixture so there's no other material in contact with the back side of the joint. We will weld the first side and then turn it over, back grind the second side prior to second side welding. To give you a better picture of how the weld bead sets up and how the material flows, we'll be using a high dynamic range video camera to get close-up shots of the weld puddle. It's important to remember the fluidity of copper-nickel welding, similar to other nickel-based alloys, is much more sluggish than it is with carbon steel or stainless steel, and therefore puddle control and wire feed is very, very important. In addition, with copper-nickel alloys, we want to be sure that the wire never gets out of gas coverage from the gas cup, and we'll show you all that as the welding progresses. We're ready to start welding. Our welder will tack weld the ends of the plate and a few spots in between. We are using the same tungstens that would be used for stainless or carbon steel, so there's no difference in that. Once the tack is made, the welder will hold the gas on the part to assure that it cools without picking up oxide on the surface, which could later lead to porosity.
The cup size should be as large as practical, provided it does not interfere with welder visibility. A gas lens often improves the gas protection and can allow extending the electrode for welding in areas of tight access.
It may be necessary with copper-nickel alloys to use more tacks than you would use for stainless steel or carbon steel due to expansion and contraction issues, and that's why we use a pretty narrow spacing between our tack welds. Once the tack welds are complete, welder will wire brush to remove any oxides or smoke, again using a stainless steel brush that has not been used on anything but copper-nickel or stainless steel. And he'll inspect the tacks to make sure there's no porosity or cracks, and then we'll proceed with welding.
The torch should be held at about a 15-degree angle back from the direction of travel, and filler metal about 90 degrees from the torch or 15 degrees off the workpiece. Tilting the torch to a much greater angle tends to reduce the shielding gas protection, and the filler metal should always be held within the inert gas shield area. If the filler metal end becomes oxidized, the end should be cut off.
Now that the root pass is complete, we'll wire brush it to remove any oxide or smoke on the surface, and we'll inspect to make sure that we have good fusion, no cracks, no porosity or anything else that would interfere with putting in the second pass. And then we'll start our second pass. As you can see, this weld is very even with good fusion to the sidewalls, and we're ready to start welding our second pass. We've completed our second pass. We're ready now to start the third pass of this weld. Note that we're using 3/32 diameter filler metal. Obviously larger sizes could be used to make bigger welds. There's no limit on the number of passes. We don't worry about heat affected zones with this material. All we need to do is to make sure that that second pass is well fused with no overlap, no cracks and no porosity. And if there are imperfections in that second pass, we need to grind them out and repair them before we start the third pass. Okay, we've finished the first side of this weld. We've turned the plate over to prepare the backside for the final weld. As you can see, the backside is oxidized because we did not use any kind of purge. So we will clean all the oxide off. As you can see, we've removed the surface oxide. We still have a little bit of black area corresponding to the root face of the back. We're going to grind that out now with a hard wheel, again paying attention to the fact that we only use wheels that have been used on stainless steel or on copper nickel. Never use a wheel that's been used on carbon steel. Now that we've made the groove, we're going to go back over with the sanding disc and take off any of these burrs on the edges. You'll notice that we have a very nice U-groove contour. Now we've completed the back preparation. Welding of that backside will proceed just the way we did the front side, so we're not going to be showing it in this segment.
In addition to these video presentations, there is also free printed and downloadable literature covering all aspects of copper-nickel alloys, including fabrication, welding, and corrosion resistance.